Okay. We had looked at synchronous machines in terms of their constructional features, in which we had talked about winding factor, which is consisting of distribution factor and pitch factor. Then we had looked at equivalent circuit. Then we had also looked at when a generator is synchronized with the bus bar. So, how synchronization is done. Then we also talked about how a synchronous machine can work as a motor. What are all the different types, right, like a permanent magnet synchronous motor or wound field synchronous motor. So, we had looked at these two mainly. Then I had also talked about starting of a synchronous motor. Then ultimately we had also talked about phasor diagram of a synchronous motor. This is where we stand. In fact, phasor diagram we discussed for both generator operation and motor operation, both. Now, the next topic that we are going to take up will be on power angle relationship of a synchronous machine. I think we already said that if it is motor, we are going to have invariably E lagging behind V, that is the rotor side flux. Because of that, whatever is the induced EMF E, that is going to lag behind V, which is the applied voltage. Whereas, if we are looking at generator, right, if we are looking at generator, we are going to have E leading, because this is the induced EMF which is the root cause for any voltage that is appearing at the terminal. So, this will be leading whatever is the terminal voltage. This is the terminal voltage V. So, if we try to draw the overall equivalent circuit, we should be normally drawing a resistance which is actually the resistance of the armature winding or stator winding, and then we are going to have an inductance which is actually known as the synchronous reactance, which will consist of the mutual inductance between the armature and field plus whatever is the leakage, if I may call that as the leakage. So, XL and XM put together will be XS, and I am going to have on one side maybe the terminal voltage that is appearing if it is a generator, or the terminal voltage that I am applying if I am looking at it as a motor, and I am going to have the induced EMF here on this side, which is E angle delta, if I may call this as generator, where delta will be positive. If I am going to talk about this as E angle minus delta, in which case this is going to be corresponding to motor. So, this is for generator, whereas this is for motor, right. Normal values if you look at, even if it is a kVA rated synchronous machine, I am normally going to have RA about 2 to 5%. What I mean is 0.02 to 0.05 per unit is going to be the normal resistance value. And if I look at XS, it will be anywhere between 80 to 100%. Please note, this is very, very high because XM is also part of this XS. So, I am going to have essentially this to be 0.8 to 1. Whereas, if I look at MVA rating of the machine, normally we will have this RA to be less than 1%. It can be 0.005, something like that. It is going to be really, really small. Whereas, if I look at what is XS, XS will be 100 to 110% or 120%. So, you can imagine this is really, really small as compared to this. In both the cases, it is even more so in MVA rating. So, we can afford to neglect this. There is nothing wrong in neglecting the resistance. So, if we are actually drawing the equivalent circuit without the resistance, I am simply going to have this JXS and I am going to have a voltage Vt on this side, and if it is a motor, for example, I am going to have this as E angle minus delta. This is the equivalent circuit for the synchronous machine where we have neglected RA. So, we are assuming RA is negligible, which is justified. Now, if it is a motor, I am going to have the current flowing from here towards the induced EMF side. So, this is stator current Is. So, if I try to write the equation, I should write Vt angle 0, especially if I am assuming that this is connected to an infinite bus. I am going to assume that the voltage is going to be my reference vector. So, I can write that as Vt angle 0 without any problem. Now, Vt angle 0 minus E angle minus delta is going to be equal to Is. I do not know what power factor angle is going to be there in this, multiplied by Jxs. So, this is going to be the equation which is essentially the KVL I have written for this particular loop. So, I can write Vt angle 0 minus E angle minus delta divided by Is angle phi equal to Jxs. But when I write the power per phase, I can write V multiplied by Is multiplied by cos phi. This is going to be the power that is being absorbed by the machine. So, this is transported from the infinite bus towards the machine if it is a motor, and it is going to deliver it in the form of mechanical power. So, let me write this as P per phase. But for 3 phases when I write, I should write P total equal to 3 V Is cos phi. This is going to be the 3 phase power in general. So, I can write actually this V is same as Vt. I hope you understand that this is essentially the terminal voltage. So, I can say Is cos phi s will be the real part of Vt angle 0 minus E angle minus delta divided by Jxs, right. Now, I should be able to, let me write this as cos phi itself, not cos phi s. So, let me write this as cos phi because I have used only cos phi as the power factor. Okay. Now, I can write Vt angle 0 minus E angle minus delta. I should be able to write this as Vt divided by Xs, and this is 1 divided by j. This will be essentially minus j, and I am going to have E angle minus delta, right. So, E, this can be written as cos delta minus j sin delta, right, divided by Jxs. So, this will be E cos delta divided by Jxs. So, I can write minus E cos delta divided by plus Jxs, because of which I should be able to write this as minus j Vt by Xs plus j E cos delta divided by Xs, and I can cancel out this j with this j, and minus into minus is plus. So, I should be able to write this as E by Xs multiplied by sin delta. So, if I want to look at the real part alone, this is the only real part that is present. Please note this is plus. I have written this as minus, this is actually plus. So, this is going to be the real part that is available. So, let me write the power what I have written as the total power, which is 3 V I cos phi is equal to, we just wrote I cos phi is real part, which is E Xs by sin delta. So, I should be able to write this as 3 V E sine delta divided by xs. So, this is essentially known as the power angle relationship for a synchronous machine. So, this delta, which is the angle between, if I say this is actually my V or Vt, and let us say I am going to draw a current which is Is and which is having a phase angle of phi, I should be able to write that I times xs will be somewhat like this. This is what will be jIxs, right. So, I have to essentially write the same thing in the opposite direction, which will become minus jIxs. So, Vt minus jIxs will actually give me what is known as my E. This is going to be E, and this angle is delta. So, I can write this as this is E angle minus delta. Please note, E is lagging behind Vt in a motor. So, I am essentially having the relationship Vt minus jIxs equal to E angle minus delta, and this particular delta, which is the phase angle between Vt and E, plays a very vital role in deciding how much power is being delivered by the machine. So, this delta is generally known as power angle or torque angle or load angle. All of them are synonymous with each other. So, this plays a very vital role in deciding how much is the power delivered either by the synchronous motor in the form of mechanical power or by the synchronous generator in the form of electrical power. So, we are looking at this as a very important thing. Now, when I have actually, let us say, a motor which is working at a particular delta, let me take some value, maybe delta is 5 degrees. Currently, maybe the machine is delivering 70% of rated power. Okay? Let me assume it is a 1 MVA or 1 MVA generator or motor, and it is generating only 700 kVA or kilowatt. That is all it is generating. Okay? Now, if suddenly, if it is a motor and I have increased the load to full value, maybe I have just increased it to 1 megawatt suddenly. Now, what will happen is, instantaneously, I am not going to be able to increase the current or increase the voltage, nothing can be done. Actually, assume that the machine is connected to the infinite bus. So, this is the infinite bus, and here is where my synchronous motor is connected. Okay? So, this voltage and 50 hertz both are set in stone. I cannot change them. Now, when I increase the power delivering capacity from 700 kilowatt to 1 megawatt, I have increased the load. Immediate response of the machine will be to release the kinetic energy. So, I am going to see that the kinetic energy stored in the rotating parts will be released. When this is released, speed is going to decrease. So, omega m, let me call this as omega m. So, mechanical speed, this is going to decrease. Because the speed decreases, now please look at the phasor diagram. This corresponds to the rotor, whereas this corresponds to the stator. The stator frequency is set in stone, that is 50 hertz, whereas the rotor speed is not set in stone, that depends upon at what velocity the rotor is rotating. We said that the rotor speed has come down. Maybe originally it was rotating at 1500 RPM. Now, maybe it has come down to 1490 RPM. Now, between omega s and omega m, there is a difference. Multiplied by t is going to be the angle change or change in delta. So, delta is going to be this. So, what will happen is, originally my delta was 5 degrees, Now slowly it will start increasing, it will go to 6 degrees, 7 degrees and so on and so forth, it will be increasing. So what we wrote as P total, which is 3 E V divided by XS sin delta, if you look at V, that is a constant, maybe E is also a constant because I have not changed the frequency, I have not changed the excitation. Please note E is equal to 4.44 F phi number of turns multiplied by K winding factor. This we derived a few classes ago. The flux will not change if I do not change the excitation. Frequency cannot change because it is connected to infinite bus. Number of turns cannot change because it is the structure of the machine. Same is the case with the, oh, this is not going. Same is the case with the winding factor of the machine as well. So, I am going to have essentially only thing the P total can change with is with delta, and delta has increased. So, P total will definitely increase. Please understand, the kinetic energy was released because what was the P generated by the machine was less than P demanded from the load side. Now, P generated from the machine is slowly increasing because delta is increasing. So, if I look at actually how the power is changing, I should draw the variation somewhat like this. If this is delta and this is power, I am going to have increase in the power as delta increases. There is no doubt about that, right? And the maximum power probably is somewhere here, which will be much higher than even 1 megawatt. So, probably originally it was operating somewhere here and it is moving in this direction. Okay. Now, the angle delta is increasing further and further because 1500 minus 1490 RPM multiplied by T is delta delta, and as time progresses I am going to have increase in delta further and further. So, if it has started from here and if it is 1 megawatt point is somewhere here, it will even overshoot that and reach a point where maybe it is generating 1.2 megawatt or something, and at that point because P generated becomes greater than P demanded, I am going to have the machine accelerating or accumulating some kinetic energy. So, from 1490 it will go to 1500 and it might go to even 1510. When it goes to 1510, what will happen is, now here delta delta was increasing or positive, whereas now when the speed becomes 1510, 1510 subtracted from 1500 is going to mean negative velocity, which will make actually delta delta negative or decreasing. When it is decreasing, now again the machine will start moving in this direction. So, I am going to have reduction in the power that is being generated. So, it might reach a point where it reaches here. At this point again the machine will realize that P generated is smaller as compared to P demand. So, again the machine will be decelerating or retarding. So, what will happen is, you will see that under this condition, delta probably was at 5 degrees, it increased, then it will decrease, then increase, decrease and settle at a particular value. Whatever is the value at which P demand will become equal to P generated. So, this is essentially delta variation versus T, right. You can even call it as delta delta versus T, that is also fine. But when you actually look at the speed will also actually, it would have started from less than synchronous speed, it would have increased, decreased, increased, decreased and ultimately settle at synchronous speed itself. This is omega s. So, we are talking about omega m, how it is changing with respect to time. So also will be the torque. Torque will also go from positive to negative, or power will also go from, if I want P demand, initially P generated was less, then it would have gone increasing, decreasing and so on, and ultimately it will settle down at P demand itself. Now, this oscillation is generally known as hunting oscillation. Hunting is a very, very common phenomena that is seen in any synchronous machine if there is a variation in the frequency. So, if the frequency changes, I am going to have simultaneously omega s changing. This will also increase or decrease depending upon frequency change. Either frequency changes or load changes. In either case, you would see hunting oscillations always occurring in a synchronous machine. And this hunting oscillation is not good, especially if I am looking at very critical loads where even small vibrations cannot be tolerated. Even small vibrations cannot be tolerated, then I would like to eliminate this hunting oscillation. That is why we use something called damper bars. The damper bars have two purposes. One is to damp out hunting oscillations. In this particular case, because the damper bars are very similar to induction motor winding, if I look at the induction motor torque, please note, if I am looking at this speed as omega s and I am drawing this as omega and this as torque, right, this is the torque, I am going to have anything below synchronous speed, I will have a positive torque. Anything above synchronous speed, I will have a negative torque. So, the torque that is generated by the damper bars, which is very similar to the squirrel cage bar, that will always be pushing the motor or rotor to reach synchronous speed. So, its major job is to push the rotor always to attain synchronous speed. So, damping out the hunting oscillations is very effectively done by the damper bars. The second purpose of damper bar, which we discussed already, is to start a synchronous motor. This we talked about earlier as induction start synchronous run motor, if you may recall. So, this is another purpose of damper bars, presence in the case of a synchronous machine. One last topic I would like to take up before I finish synchronous machine is that V and inverted V curve or power factor control of a synchronous machine. We said that one of the major advantages of the synchronous machine is to have a power factor control. What we meant was, because excitation is given from the field side or rotor side, right? I can make it in excess, I can make that less, or I can make exactly whatever is needed. So, we said if this is just sufficient, then the machine is going to work at unity power factor. If I am going to give excess excitation, which means I am giving excessive amount of reactive power, in that case we will return some reactive power to the mains, which means it is going to act like a capacitor. So, it will be a leading power factor machine, especially when it is functioning as a motor. And if I am going to have the excitation slightly less or there is a shortfall, then I might have to draw some amount of reactive power from actually the grid, which means I will have to make the machine function as an inductance. So, we are going to see a lagging power factor for the motoring operation of the machine. Let us try to analyze this with the help of a phasor diagram. So, let me first draw, maybe the machine is connected to infinite bus. So, I am going to have essentially this as my voltage. Please note, this is connected to infinite bus. So, it has to have the same magnitude of voltage and same 50 hertz frequency. It cannot change. Under this condition, let us say I have a current like this. I am going to show this as IA1. I am talking about the first condition of the current, and I am showing a lagging power factor current. Okay? Now, I am talking about V and inverted V curve. So, I have to talk about this at a given power. So, I am showing the locus of constant power locus for the current. So, IA locus for constant power. So, what I mean is IA cos phi is somewhere here, right. If I draw IA cos phi, this is how it is. So, Vt multiplied by IA cos phi multiplied by 3, that is what is my real power. So, irrespective of anything, the real component of current, the length has to be only this much. That is what we are trying to say. Now, this is lagging power factor condition. Let me call this condition as IA2, which is unity power factor condition, and I may have one more which is actually leading power factor condition, which I am calling as I3. So, which is actually phi 3. Let me first of all complete the phasor diagram corresponding to this IA1. So, if IA1, if I have to draw the drop, it is going to be IA times JXS corresponding to this IA1 here. If I subtract this quantity from Vt, which I have to draw it like this, which is actually parallel to this. So, let me draw it like this. This is what is minus JIA1 XS. Then I should be able to draw this particular point as E1. This is the excitation voltage corresponding to the first condition where I am having a lagging power factor phi 1. Okay. Let me try to draw this corresponding to IA2 now. If I try to look at IA2, I have to draw perpendicular to this, which will be actually IA2 times JXS. I want you to notice that IA1 is much longer than IA2 because this is like hypotenuse of this right angle triangle, whereas this is the adjacent side of this right angle triangle. Obviously, I am going to have IA2 much less than IA1 because IA2 happens to be IA1 cos phi 1. Cos phi 1 definitely has to be less than 1. So, I will have IA2 less than 1. Now, if I draw this IA2, I have to draw it like this. This is what it is. So, this will be minus JIA2 XS. Right. Now, if I draw the resultant Vt minus JIA2 XS, I will have it like this, and this is E2, and E2 is definitely longer than E1, and I can also draw the angles. This is delta 1, whereas this is going to be delta 2, right, corresponding to the second condition. Now, E1 and E2, if I compare, I said E1 is smaller than E2, but any E is equal to 4.44 F phi number of turns multiplied by kW. Only thing that could have changed is phi. So, if I write about E1, this will be phi 1. Whereas, if I write about E2, this will be phi 2, rest of the things being same, right. If E1 is less than E2, then I should have phi 1 less than phi 2, which means the field current in the first case must have been smaller than the field current in the second case. So, as I increase the field current, the machine moved from lagging power factor zone to unity power factor zone. Let me look at the leading power factor zone as well. In the leading power factor zone, I should have had IA3 JXS somewhat like this. So, I should have had it like this, it should have been longer actually, right. So, correspondingly I should have drawn this particular quantity which is minus JIA3 XS, this is that quantity. Now, if I have to join this, I have to join it like this, this is what is E3. So, I should say E1 is the smallest, then E2 is higher and E3 is the highest or largest. So, clearly I am going to have phi 1, the flux is the smallest in the first condition, then phi 2, then comes phi 3 which is the largest condition. So, as I increase the field current from IF1 to IF2 to IF3, the power factor moved from the lagging zone to the unity power factor zone to the leading zone. And this if I try to plot in the form of how IA varies with respect to IA varies with respect to IF. So, I am trying to look at the field current. So, initially it was at lagging power factor condition, but it was drawing a longer or bigger current. When it was at unity power factor condition, it was drawing minimum current. When again it moved to leading power factor condition, it drew a current which is higher. So, I would say IA2 is the minimum armature current, right. So, when I draw, I should show it as though at a particular point it becomes minimum armature current, and in either of the field current side, it is going to be higher than the minimum armature current. So, if this is my minimum armature current, this is IA minimum, this will also correspond to UPF condition, unity power factor condition, whereas this will be lagging and this will be leading. This is corresponding to a synchronous motor. So, the over excited or excessive excitation condition of a synchronous motor will always result in leading current. Let us say this corresponds to a particular power P1. If I increase the power further, I will again get some other armature current corresponding to that higher power condition. So, IA minimum for P1 will be definitely smaller as compared to P2 if P2 is greater than P1. So, I should draw one more graph which is probably like this, right. So, this is corresponding to P2, whereas this corresponds to P1. But if this is the field current corresponding to, let us say this is IF1, for P2 I would have the minimum armature current corresponding to IF2, because to generate P2 power which is greater than P1, in all probability I will require a higher flux. So, normally I would say IF1 is going to be smaller than IF2, which is actually minimum armature current condition, right. So, they are not going to happen at the same IF, it would rather attract a larger flux or larger field current whenever I am demanding a higher power. On the other hand, I should be able to draw how the power factor changes again with field current. This is pretty clear, I suppose, because unity power factor occurs at optimum value of field current. So, I can draw it somewhat like this. So, this field current is the one or IF1 which is corresponding to unity power factor condition, whereas this will be lagging and this will be leading. Let us say this corresponds to P1, a particular power. If I am talking about P2, we said IF2 will be the optimum current corresponding to the higher power condition. Then correspondingly, please note the power factor cannot be greater than unity. So, I have to essentially draw it corresponding to this as though this is the way the other curve is, and this curve corresponds to P2. The first curve corresponded to P1 and this curve corresponds to P2. So, the V curves for the synchronous motor or synchronous generator are always drawn between IA and IF. IF in the x axis, which is the excitation current, IA is the armature current drawn from the stator side. And inverted V curves are always drawn between the power factor on the y axis and field current on the x axis. What is kept as constant is the delivered power, be it motor or generator, it does not matter. We are essentially talking about the power to be held as a constant. Now, because we said resistance is negligible, there is hardly any real power loss that we are talking about, then we will call almost the efficiency to be 100%, which defies the second law of thermodynamics. No machine can have 100% efficiency. So, whenever we do the efficiency calculation, we will normally consider RA. So, RA should be considered or RA should be taken into account, whereas whenever I am not doing efficiency calculation, most of the times we may neglect RA, right. So much so for the V and inverted V curve and hunting oscillations of the synchronous machine. Let me try to work out one problem on synchronous machine, which will also give you a feel for what is actually regulation and so on and so forth. So, let me take up the problem statement. So, this problem statement is somewhat like this. A 3-phase 5 MVA 11 kV 60 hertz Y connected synchronous machine has negligible RA and XS equal to 10 ohm. Okay? And we have said it is already connected to a 60 hertz bus. So, we do not have to take the variation of XS at all. Okay? The machine is connected to a 11 kV 60 hertz bus or grid. Okay? If it is delivering a power of 1 megawatt as a generator, calculate E and delta. Of course, I have said 1 megawatt at 0.8 power factor leading. Okay, this is the first question that is being asked. Okay. There is a second question. Instead, if the machine is working as a motor at 1 megawatt 0.8 power factor leading condition, calculate E and delta. Third portion is assuming that condition 2 is at rated excitation. calculate delta IA and power factor at 80% excitation and 1 megawatt output for motoring operation. Okay. Let us try to work out the solution. So, let me start with first of all calculating the rated current. Easiest is to do that. So, rated current, it is a 5 MVA alternator, root 3, VL is 11 kV. So, I should be able to calculate what is the current. So, 5 into 10 power 6 divided by root 3 into 11. So, this is essentially 262.4 ampere. This is coming out to be the rated current. Now, let us try to look at what is the condition at 1 megawatt power. And this is also given 0.8 power factor leading. Please note, whenever you are calculating the power, whether it is lagging or leading, it is not going to matter. So, 1 into 10 power 6 divided by root 3 VL cos phi, right. So, I am going to get 1000 divided by root 3 multiplied by 11, because 11 into 10 power 3 and 1 into 10 power 6, I have cancelled 10 power 3 multiplied by 0.8. So, this is coming out to be 65.6 ampere. I have to write the phase angle as well, that is about 36.9 degrees, cos inverse of 0.8. Okay. This current is leading the voltage, that is what is given. Okay. So, when this is functioning as a generator, I have to write Vt plus Ia angle phi multiplied by Jxs will give me E angle delta. Please note Vt, because it is star connected, I have to write 11,000 divided by root 3. If I miss out this root 3, it will be a problem, right, per phase voltage. Always the equivalent circuit, all the equations are per phase equations. Okay. Now, this is 11,000 by root 3, Ia is 65.6, angle 36.9 degrees multiplied by J 10, right. This comes out to be, I think, 5980 angle 5.03 degrees. Please note, this is coming out to be plus, delta is positive. So, it is clearly generator operation. 5980 is smaller than this Vt, whatever we got. This 11,000 by root 3 is 6351 volts. So, I am going to have actually, under this condition, I can calculate regulation. Although this is not asked, I am just calculating it. Regulation is, what is the open circuit voltage minus the load voltage, rather the other way around, load voltage minus open circuit voltage, right. It is load voltage or terminal voltage minus OC voltage divided by, I can say, rated voltage. So, here load voltage happens to be 5980 and this voltage happens to be 6351 if I am talking about generator. So, this is what I am talking about, divided by rated voltage. Please note, the terminal voltage happens to be higher than the generated voltage, which will happen under leading power factor condition. Normally, any leading power factor condition is going to give rise to a higher voltage at the terminal. You had seen this in transformers as well. So, this is essentially negative voltage regulation. This is because of leading power factor condition. Okay? This is an additional point I just wanted to mention. Now, let us try to work out. So, from whatever we got, we can say E is 5980, delta is 5.03 degrees. So, these two have been solved. Now, let us try to go to point number 2, where the same 1 megawatt is delivered under motoring condition, under 0.8 power factor leading. All you need to do is, you have to say Vt, right, angle 0 minus Ia angle phi jxs gives me the back EMF or induced EMF, E angle delta. Here delta will automatically come out to be negative. So, we said 11,000 divided by root 3 minus Ia we had already calculated, Ia will not change, that is still 65.6. So, 65.6, right, angle 36.9 leading power factor multiplied by J10. So, if you try to calculate this, I think this comes out to be 6765 angle minus 4.45 degrees. Please note, in the previous case delta was plus 5.03 degrees, whereas in this case delta happens to be minus 4.45 degrees. And similarly, this happens to be E, whereas in the previous case the E was only 5980. Okay? Now, in this case only these two are asked. In the third case, still we are going to have 1 megawatt of power, but excitation is decreased to 80%. Previously excitation was 100%. Now excitation is 80%. Now what is being asked is what is E, what is delta, what is the power factor, what is I. Everything is being asked. Okay? Now here we got E to be 6765 volts. And this is proportional to the flux or IF. When it was 100% flux, I had 6765 volts, right? When it is 80%, I am going to have E nu is going to be 6765 multiplied by 0.8 volts. So, that comes out to be 5412 volts. Okay? Now, one more thing we said was 3VE by XS sin delta, which is also equal to 3VI cos phi. We said normally I cos phi is a constant whenever power is constant. Similar thing we should be able to say E sin delta is constant, because Xs is dependent upon the frequency. Infinite bus Xs will be a constant. V is connected to infinite bus, so that is also constant. So, only thing is E sin delta is dependent upon the power. So, if power is a constant, E sin delta is a constant. I would like to emphasize that from the phasor diagram what we drew earlier, if I try to look at what is E sin delta, this vertical distance, this will be E sin delta. This E sin delta will be a constant as long as power is a constant. Okay? So, let us try to now look at what had been E sin delta in the previous case. This is E delta. So, E sin delta will be E sin of minus 4.45 degrees. This came out to be something like 524.8 volts. Okay. So, I should say in this case also 5412 multiplied by sin delta nu magnitude is going to be equal to 524.8 volts, because E sin delta has to remain as a constant. So, delta nu happens to be now minus 5.56 degrees. From here you should be able to solve for this, right. Once you have got delta nu, this is pretty simple now. Because I know delta nu, I should be able to say E angle delta in the new condition, which is 5412 angle minus 5.56 degrees is going to be equal to Vt angle 0 minus J XS Ia nu phi nu, right. So, you would get basically there is one real part and one imaginary part. Similarly, you will be able to get one real part and one imaginary part here. So, I would say 10 Ia cos phi happens to be 524.8 and 6351 plus 10 Ia sin phi happens to be 5386.5. What I mean is this will be equal to 5386.5 plus j, not plus j, minus j 524.8. Okay. Now, from this I should be able to solve for cos phi as well as Ia. So, Ia happens to be 109.8 ampere and phi happens to be minus 61.46 degrees. This is lagging clearly. Please note, by reducing the excitation, the machine has moved from leading power factor condition to a lagging power factor condition. This cos phi may be something like 0.45 or 0.43 or something like that. So, it has really come to a very, very low value of lagging power factor condition. This tells that this is under excited condition, whereas that was over excited condition. The original one what we saw was over excited condition. So, this is indirectly showing how V or inverted V curve works. So, on the whole, we have completed whatever we had to do in terms of synchronous machine. We had started off with its constructional features, we had looked at its equivalent circuit, we had looked at winding factors and so on. Then we had looked at synchronization, then we had derived the power angle equation, Hunting oscillation. We had also looked at V and inverted V curve, and on the top of that we had also looked at one of the problems, how to work out. Thank you so much for your attention.